I wanted to sort of pitch or present the work today in the context of the effects of stress because of the high burden that mental illness has on young people. That is, as many as 40% of young people today experience a mental illness. The majority of these are related to anxiety and stress. And if we don't treat these early, they can go on to lead to chronic illness, both psychiatric as well as physical illness. So the questions that we've been asking in our laboratory over the years is how are these early life experiences impacting emotional well-being and the underlying brain circuitry involved in that well-being? And ultimately, what we need to do is to use this information so that we can facilitate and enhance healthy brain development and also, of course, well-being of young people, which is then going to be well-being of our society. But if we first take just a simplistic look at all the changes that are happening in postnatal development, what you'll see is that there is dramatic changes just in the number of synapses throughout the brain that develop regionally. So we see a proliferation and a subsequent pruning of these connections. Simultaneously, there are changes in neurochemicals and neurotrophins that are absolutely essential to development and learning. And with all these regional changes, it is co-occurring with increased myelination throughout the brain, which is making the connection stronger. So we've been focused on all these dynamic changes and trying to understand with just one picture using human imaging and focusing on one circuitry that's really important for our ability to process emotional information, so emotion regulatory and emotional reactive processes. And during this time, during childhood and adolescence, there are major changes in this circuitry, and we think that they will are one pathway for us to seeing how early life experiences are reflected in them and how this continued development may also be a window of plasticity of sorts, where we may have the biggest change. Now, in human studies, one of the ways that we try to look at this in these circuitries and the behaving human brain non-invasively is to use simple stimuli or cues that we present. So here's an example of a cue with emotional information. We examine how these cues impact both brain and behavior. These cues can be positive, smiling faces, or negative, or they can be neutral. But what we see is, even if you were in the laboratory performing this task, if we asked you just to press a button whenever you saw one of these cues, you would be significantly longer in detecting a threat cue, a fearful cue, than you would be to a neutral happy, as you see here. So we have a longer latency there. It's adaptive when we see cues that have some uncertainty or ambiguity. I don't think for a minute when I present this cue to you that you are threatened by that. However, we learn over a lifetime when we see cues like this that there might be potential danger. And what's very important for us to understand is, in this context, is it a threat? So if a bear were to come into the room, I might have an emotional response. But the circuitry is important if I saw a bear in a zoo to know that that bear in that situation, I would be safe because they were behind a cage or wire. So now, if we look at these responses and this change in our responses depending on the potential threat of information in our environment, if we open up the brain and look inside, the areas that tend to be related to that delay in our approach behavior in such situations involve the amygdala and the prefrontal cortex. And hopefully what you note from this slide is that the amygdala, the more active it is, the slower you are to respond. The amygdala is very important in picking up the emotional significance of information in the environment and has been associated with emotional reactivity. In contrast, The prefrontal cortex, which has direct projections to the amygdala based on elegant animal work and more recent human work, that area is less active when you're really slow to respond, and the more active it is, the quicker you are. That is, you see a potential threat, you are able to understand in this particular situation with repeated presentations of it, get over yourself, all right already, nothing's going to happen to you. Now, I've just made a sort of claim that over time, nothing's going to happen to you. Well, let's look at that in the brain and what systems are absolutely essential for that. What's important when we look at, with those repeated presentations, how well you habituate to these cues, is this inverse coupling between the prefrontal cortex and the amygdala in the circuitry. And this inverse coupling or negative connectivity seems to be changing radically from childhood to adolescence. And it is when you are not able to habituate that response that is associated with heightened anxiety. So I just want you to focus on this quadrant for a moment. And basically, if you look over at the y-axis, that's amygdala habituation, and it's a negative score. That means not only was there not a change in how active the amygdala was to these cues, but that it was actually sensitized, and it was increasing over the course of the experiment. And that's related to the highest level of self-reported trait anxiety. Now, some of these pictures had a lot of data, and I think data, slides and pictures are worth 100 or 1,000 words, but movies might tell a simpler story. So this is an example of an individual who reports low anxiety, and they're being presented with these cues of potential threat. So you'll see there's bilateral activity in the amygdala with repeated presentations, but then it's like the system begins to return to baseline, and it turns blue. That represents from the increase going back down to baseline. In contrast, when we look at an individual with high anxiety, we basically see a similar pattern at first with this bilateral activation of the amygdala, but then it stays up, and it stays up, and it stays up, and it doesn't return to baseline. So it's that vigilant state of anticipation of threat and an uncertainty of what these cues potentially mean. So two different paths that we've taken in trying to understand these two very different neural signatures here is to look at differences in genetic factors that may explain this, but in the interest of the symposium today, also in the environment or experiences that we have. So how does early life stress impact the development of this circuitry? And we have used really an extreme example of early life stress. It is an unfortunate but a natural occurring one, and that is children who grow up in the orphanage. Now, in the orphanage experience, all the orphanages vary, but there's always going to be some fragmented caregiving because of the high ratio of so many children to a single caregiver. So what we've been interested in is, as these children are adopted to families in the United States, we've been trying to understand how this dysregulation of their needs not being met, how there's not attunement in the child's needs with what the caregiver can actually provide to them, how that impacts their ability to regulate self, but particularly today I'll talk about how to regulate emotion. So again, we use these simple cues, and we ask children who have been adopted from the orphanages, as well as comparison group who have not been adopted, who live in the United States. They all have moved, the adopted children have been here for at least 2 years to make sure they get acclimated to their new home and their new culture and environment. And what we do is we present these cues of potential threat, but in the task we tell them, ignore these, try not to pay attention to them. And you find in the situations in which you have these cues relative to situations where you present a smiling face, that the adopted children are much slower in anticipation of one of them occurring. So even if it's a neutral face on the screen, if they know they're about to see a threatening face, they're really hesitant to respond. But if it's to a happy face or smiling face, you don't see a difference between the two groups. Now this is paralleled in the brain by enhanced activity in the amygdala. And that's shown here on the left and the right side. But I think what's important about these findings is, first, this is greater activity in the children who are adopted from orphanages abroad relative to the comparison group, the area in blue is actually more active in the comparison group. This is a part of the brain that's important for attention regulation and emotion regulation. So one is being able to regulate their emotions and ignore, and the other is quite reactive, that group. But more importantly, when you see images like this, and you have these neural signatures, it is, how does that relate to their actual behavior when you get them outside of the scanner environment or the laboratory? And so we measured how the behavior between caregivers and their adopted children when they had been separated briefly and then they were reunited. And we looked at the amount of eye contact they had with their caregiver when they were reunited. And basically we see that the more active the amygdala was, the less eye contact they had with the caregiver. Also, the less eye gaze they actually held on the faces that they were presented in the experiment as well, too. Now, when we have natural occurring experiments such as this, we don't really have control on pre-existing conditions that may be there, genetic or environmental. So we've actually turned to use mouse models to try to see if we can control for the genetic and environmental confounds that might otherwise explain what we're seeing. And so we borrowed paradigms that have been developed by individuals like Regina Sullivan at NYU and also Tali Barham at UC Irvine to induce sort of a fragmented caregiving of a dam to her pups. And so I want to just show you those movies. On the top is a dam where we've taken away the nesting material. She has a little bit, but not sufficient. So she is running around. Oh, this is not in real time. she's even a little bit slower than that. So basically, I don't even know if you can see the control dam. So she has all the nesting material she needs, and she's spending the majority of her time grooming and feeding, nursing her pups. But you can see the mother above is trying to pull together the nesting material and sometimes her pups over to her corner for the nest. So basically you're seeing this fragmented care because she can't attend to her pups when she's doing other things, which we thought might in the slightest way mimic some of the fragmented care that we see in the orphanages. And if you look within a 2-hour period, you see a significant difference in the amount of time that the dam is spending with her litter relative to controls. But quite frankly, if you look across a 24-hour period, they're spending almost as much time with physical contact, but it's very fragmented in that contact. So there's not that attunement between the caregiver and the pup. So then if we look at their ability to regulate their emotions, not the dam, but now her offspring who've been given this fragmented care, basically what we see in a paradigm in which we've trained them that a nozzle will lead to them having access to condensed milk, and mice love condensed milk. And so we put that nozzle in a novel cage with a bright light where there's potential threat for mice. And we see that when we put it there, there's a difference between those mice that grew up with the stressed dam relative to the mice whose dam, their mother was not stressed. And you don't see any difference in terms of how quickly they move to the nozzle in their home cage. And then if we look at the brain using CFOS activity as an index, we see heightened amygdala activity in this group relative to the controls. And so this gives us a bit more confidence that what we're seeing in the human data that I presented is not as much associated with maybe pre-existing conditions as it is with the early life stress, because these parallel quite nicely. Now with the mice, unlike our human children who are usually adopted by super parents, if you do nothing after that, you see that there's persistent effects of that early life stress, so that they're still showing heightened amygdala reactivity in adulthood, even though there's continued development of the circuitry. Now, this persistent effect in these mice is somewhat reminiscent of work that Nim Tottenham has done at Columbia in collaboration with Dylan G., who's now a colleague of mine at Yale University. And she's actually shown that if you look at this frontal limbic circuitry, that there appears to be something similar to a premature closing of a sensitive period of neural development of this circuit, such that if you just look at healthy children, what I described before, there are drastic, significant changes from coupling between the prefrontal cortex, and it becomes inverse or negatively related in adolescence. What we see in children who have grown up in the orphanage is you're already seeing those changes early. And so now NIM is trying to follow and see just how rigid does that make the individual when they go through adolescence, which is an even more stressful time of life and meeting so many challenges. And I just want to end with one more study, an area of work that Dr. Tottenham is following up on, and that is showing how important the caregiver is. And so in these experiments where we're showing these very simple stimuli in the scanner while we're taking pictures of the brain and watching how they perform games, if you simply put a picture of the face of the caregiver along the screen where they're performing the task, and you can counterbalance that with a face of a stranger, she sees that that's associated with decreased activity in the amygdala. So it's a decrease in that emotional reactivity just by having that parental cue present there. And also, there is an increase in the or inverse coupling with the prefrontal cortex that is typical more of adulthood, but we're seeing the parent has that ability to help regulate. So I hope what I've shown you or illustrated is just one small set of experiments that are being performed where we can show that early life stress can lead to persistent changes in brain and behavior, particularly in terms of emotional capacities. And it highlights, too, this last bit of work, the importance of having very early interventions and also the importance of the caregiver in helping to develop a healthy brain, and also in terms of enhancing emotional well-being now and hopefully forward for that individual. So I just want to end by thanking so many individuals who have come through my laboratory over the years, the majority of them fellows who are stellar stars now, and to also thank you for your attention